Welcome to Lecture 8A entitled Small Signal Modeling Framework. This material comes from Reading Assignment 2, the Introduction, and Section 3.1. The objectives here are to introduce the framework for determining the time evolution of a dynamic system consisting of state variables, inputs and outputs for small perturbations about a DC equilibrium, or sometimes called operating point. The concepts and definitions developed throughout this particular teaching module include the Jacobian matrix, what we mean by system equations, which are comprised of state space equations and output equations. And then these equations themselves consist of state variables, input variables, and output variables. Again, the notion of what we mean by equilibrium or steady state or DC operating point. Points in the case that we're dealing with nonlinear systems, in which case there might be multiple equilibrium points or none at all. And then finally, what we mean by small signal equations. All right, as usual, the second slide basically just details the contents of this lecture. So we'll just move on from here and carry on. All right, so this is the first instance now that we will basically expose you to a new definition, and that is that of a Jacobian matrix, which plays a very important role in many branches of mathematics, and we'll see this Jacobian be used in a number of contexts throughout the remainder of the term. What it does is it relates the partial derivatives of the old variables with respect to new variables, which means we're dealing with transforming from one set of variables to a new set of variables. And so three examples shown here correspond to the case where in one situation we're basically just dealing with single variable case. The second case is two variables, and the third case is three variables. So in the first case, basically what we're saying is that we're going to let x be some new function of u. And in this case, the Jacobian matrix would be just the derivative of f with respect to u. And this is a scalar, all right, because this is just a scalar equation. On the other hand, if we have, for instance, two variables, x and y, we want to express them in terms of two new variables, that's u and v. Then in this case, the Jacobian matrix is defined by taking the partial derivatives of f with respect to u and v and forming the first row of a 2 by 2 matrix, and then taking the derivative of g with respect to u and v and creating the second row of a matrix. So if we write it in this form, this is equivalent to writing it this form or this form, and we essentially say this is a 2 by 2 Jacobian matrix. Thirdly, for instance, we could have three variables. So for instance, x, y, and z each being their function of u, v, and w, u and v and w being the new variables. In this case, if we want to create a Jacobian matrix, we'd be taking the derivative of f with respect to u, v, and w, and that constitutes the first row of a 3 by 3 matrix. Similarly, we would do the same with the function g, that's a partial derivative with respect to u, v, and w, produce the second row of a 3 by 3 matrix. And the final row would be basically the partial derivatives of h with respect to u, v, and w. Of course, we can write it this way or this way or this way. In any case, this would be a 3 by 3 Jacobian matrix. All right, so let's look at the types of problems in which Jacobian matrices appear, and two specific cases are shown on this slide. First one being the solving of nonlinear equations, and this is covered in Section 1 of Reading Assignment 2, which of course you're not going to be responsible for in this course. In this case, the Jacobian matrix, which is J in bold, is used in a recursive algorithm to compute the solutions. There could be no solutions, there could be one solution, or multiple solutions if we're dealing with nonlinear systems. So this is for a multivariable nonlinear set of equations, and we typically refer this as the multivariable Newton-Raphson method. For example, consider two implicit nonlinear equations in two variables. And so here's the first implicit equation, the second implicit equation, and the objective is to solve for x of 1 and x of 2 for this set of two equations with two variables. All right, so in order to solve for the variables x1, x2, we need to solve the equation x equals x naught minus j inverse. This is the inverse of the Jacobian matrix. And then f evaluated at x naught basically being the previous value or guess that you had for x1, x2 as being a solution for these two equations. And the x1, x2 subscript lowercase would be based on the next best estimate. Okay, so in one case it's the previous guess, and in the other case it's the next guess for the solution. And so you're basically taking the old values, right, and using them to basically compute the new value of x. And you do this on a recursive basis until the difference between x and x naught become vanishingly small. If we're taking the inverse of the Jacobian matrix, then again the Jacobian matrix involves partials with respect to the two variables x1 and x2. And here we of course are holding the values of x1, x2 at the previous value, which is uppercase x1 and x2. And this is of course the second row, which involves the partial derivatives of f2 with respect to x1 and x2. And fx naught would basically have this form. So this is basically in a sort of a column vector form. All right, this is for your information, but we're not going to be basically looking at this at all, and it's only in assignment 2. However, we will be looking at small signal modeling. This is in section 2 of reading assignment 2, but also appears basically in lecture 8 extracted. So this is the only material you actually need to look at, although more material is given in section 2 of reading assignment. So in this case, what we end up with are Jacobian matrices, 4 of them. These are basically JF, BF, JG, and BG, and they're used to relate small signals to each other. And this is a particular form of these equations. So you'll notice here you have a column vector involving the derivatives with respect to time of the two variables. In this case, a two-variable problem. This will be x1, x2. The fact that it has a hat means that it's a small signal, and that we can relate these derivatives to the signals themselves, again small signals, plus to input signals, u1 hat and u2 hat, again small signals. And so there's going to be a matrix multiplying the small variables x1, x2, and a matrix multiplying the input signals u1 and u2. And these are Jacobian matrices. We also would have an output equation. This output would be in terms of y1 and y2. Again, these are small signals, and these would be related to the input variables x, which we call the state variables, and the input variables, which is u1 and u2. And again, these are now involving matrices. These matrix here involving the state variables, small signals. This is a Jacobian matrix, JG, and the Jacobian matrix associated with the input perturbation signals would be B subscript G. So we have 4 different matrices that need to be computed if we're going to be looking at a small signal model. And this is in orange here. This is basic material that you will be responsible for. All right, so let's carry on. Here's another example in which Jacobian matrices appear. And this is something you'll find in section 3 of reading assignment 2. This is, of course, something you're not responsible for, but we're just putting it here so you understand the motivation for the use of Jacobian matrices. Now, in this case, if we were to take the determinant of a square Jacobian matrix, we're only going to be dealing with square matrices. You'll find that this is used to determine a scaling factor when transforming a differential length, an area, or a volume element from Cartesian coordinates into another coordinate system. And so this we'll be using this later when we, for instance, doing integrations, double integrations, triple integrations in other coordinate systems. Then we're going to need to compute the determinant of a Jacobian matrix. So let's look at some examples. So if it's a single variable case, x is a function of u. What is this done? It's used to map a point on the line u to a point on the line x. This is what the purpose of this transformation would be. In this case, the Jacobian matrix, as we've seen earlier, is just going to be derivative of f with respect to u, and this turns out to be a scalar. So this Jacobian matrix is a 1-by-1 matrix, which is equivalent to that of a scalar. On the other hand, if we have a two-variable system where x and y are both functions u and v, this would be used to map an area in the uv plane to an area in the xy plane. In this case, the Jacobian matrix would take this form, and we would end up basically taking the determinant of this matrix, and that will be the scaling factor that allows us to compute the area in another coordinate system. We can also go one step further. We can say, for instance, let's say we have an x, y, and z, and x is a function u of v, y is a function u of v, but h is a function of x and y. That z is h and x and y. This would basically be describing the equation of a surface. Since x is a function of u v and y is a function of u v, then z would be a function of u and v as well. And so this type of expression would be used to map an area in the UV plane, which is planar, to an oriented area in 3D space, which is a curved surface in 3D. In this case, friends, we could set up a Jacobian matrix of this form. It looks a little bit different. These x, y, hat, z would be basically the unit vectors in Cartesian coordinate system. These are the partial derivatives with respect to u and v. And if we were to take the term of this matrix, this would essentially allow us to compute a differential surface area element on the surface of a curved surface. We'll be dealing with this later in the course, in particular in lectures 19 and 20. And finally, we have, for instance, x, y, and z being functions u, v, and w. In this case, this will be used to map a volume in u, v, w space to x, y, z space. If we then take the Jacobian matrix, it would be a 3 by 3 matrix. And if we take its determinant, then we'll find that being a scalar is in fact the scaling factor that allows us to compute the volume of an object in another coordinate system. And lastly, the transformation of coordinates for vector operators. We are not going to deal with this topic, but nevertheless it's covered in section 4 reading assignment 2. And we'll be dealing with this later in the course, these new operators, but we just suffice to say for now, let's see what these actually represent. So the Jacobian matrix is used in the derivation of vector operators in coordinate systems other than Cartesian. And the ones that we'll be discussing in this course are the gradient operator, which operates on a scalar function f to produce a vector. We're already aware of this particular operator. The divergence operator, which again has the same symbol with a dot. It's a dot product operation that operates on a vector to produce a scalar function. And lastly, we have the curl operator, which is again this operator, and this sort of multiplication sign, which is essentially like a cross product. Well, this would operate on a vector to produce a new vector which takes on this form. We'll be discussing both of these later in the course. All right, so now we introduce a small signal framework, and we start with what we call system equations. And so what I've shown here is sort of like a box, and these x1s and x2s to xn refer to what we call state variables. We'll talk a little bit more about them. These represent the internal state of the system, such as a current through our voltage across an energy storage component. So for instance, if we talk about a capacitor, we will associate the capacitor voltage with the state variable. If we're talking about the inductor, we're going to associate the current through the inductor with the state variable. So you'll be putting inputs in. These inputs basically will sort of interact with the system, which is described in terms of differential equations, and there might be a number of outputs. Here I've made it quite generic. I said there could be as many as m inputs, could be as many as k outputs, and there could be as many as n state variables. So let's take a specific example of two state space equations, which involve two state variables and two input variables, and output equations involving two state variables and two input variables. So notice here, for instance, the fact that I have a derivative on this side of a state variable, basically completely isolated, this being a function of the state variables and the input variables. And similarly, we have another derivative equation, a derivative with respect to the second state variable x of 2, and this also is some function of the state variables and the input variables. This descriptor that you see here, or this sort of set of expressions, we call state space equations. And these x1 and x2s are internal variables. The output equation would have this form. y1 would be a function of the state variables and input variables, and the second output in this case would also be a function of the input variables, the state variables and the input variables. All right, so just as a reminder, when developing state space equation to model system, you only want one derivative to appear in each state space equation. All right, so here are two state space equations that we're dealing with here. All right, so now let's consider a systems equations example, and the problem statement is that you're given an RC circuit, which is shown on the right, and it involves a input source, it involves a capacitor, involves a resistor, all placed in series, and we have basically identified the directions of the current flow and the polarities of the voltage. These are basically consistent with the way circuit theory basically does the labeling. And we want to derive the system equations for this circuit, assuming the output variable is the power loss PR in the resistor. That's the power dissipated in this resistor. And the input variable is the voltage source V in T right here. So output is PR, input is V of N. All right, so we want to do small signal model, and so the issue would be how to go about it. So the first thing to do, which is step one, is to write out a loop equation, which means you apply Kirchhoff's voltage law. That means you sum the voltages around this closed loop. And in this case, basically, it's the capacitor voltage, that's this voltage VC shown here, which is an internal state variable. And so the V of C will end up becoming a state variable, and to be consistent with the nomenclature we've used so far, we're just going to say that X of 1 in this case is equivalent to VC, which we'll call the state variable. And at the current I of C, this is just basically the relationship between the voltage across the capacitor and the current flowing through it, is C dVC by dt. Now the current must be pointing inwards at the positive terminal, and minus, again, this is by convention. The labeling of this base is consistent with the equation that you see here. All right, so what we need to do now basically is to write the loop equation in standard state space form. All right, so this is basically how we're going to go about it. If you look down below, these are the system equations. We have basically that step one, from step one, we're going to write out Kirchhoff's voltage law, which would be the voltage drop across the resistor, which is R times the current flowing through it, which is C dVC by dt. And that voltage is the difference between this voltage and this voltage, which is Vn minus V of C. Step two basically was to write the loop equation in standard state space form. And standard space form means that equation on the left must contain only a derivative of the state variable. So we divide through by RC on both sides, leaving you with dVC by dt is equal to 1 over RC VNT minus 1 over RVC. Now this basically, in standardized form, can also be represented by some function f of 1, which is a function of V of C, right, which is a state variable, and V of N, which is an input variable. So this is more or less now in standard state space form. Now the other thing we need is the output equation, so we have the set of system equations, and so we write out the output equation in terms of the state variable and the input variable. And so the power loss in a resistor basically would be just the voltage drop across resistor squared divided by the resistance value. Well, we know that the voltage on this side is Vn and Vc on this side, so the voltage across resistor is Vn minus Vc. We square it and divide by R, and that's the power loss in the resistor. If you put this in standardized form, then this is some function of V of C and V of N. So PR, which is the output variable, is basically a function of the state variable and the input variable. Now just recall that the state variable is always associated with an energy storage component. So notice here, the capacitor is the energy storage component, and Vc was the state variable. Had this been an inductor, then the state variable would have been a current, since the voltage across the inductor is L times the derivative of this current through that inductor. So this is basically showing how we set up the system equations in the case of a simple RC circuit. All right, so this is just a quick review. System equations for a linear system. If I have a matrix, an n by n matrix, by a column vector with n entries, you obtain a new column vector with 2 entries. So for example, here, if I have a matrix of this form, times x1, x2, then effectively the way you go about doing the multiplications is you take this row times this vector, and that gives you this equation. You take this second row times this vector, and this gives you the second equation here. So in effect, knowing that the rules of multiplication of matrices look like this, we can start with this state space differential equation set. In this case, I said it's linear. Linear meaning that everything on the right here is a linear function of the state variable or the input variable. So here, for instance, these are A1, A12 are associated with the state variables, B1s, B12s, and so on are associated with the input variables. These two equations, according to the rules I've shown up here, can be rewritten in matrix form. And so what we end up with is something much more compact. We have a matrix A consisting of 4 elements times a column vector x1, x2 plus a matrix B times a column vector involving u1 and u2. And of course, this would be A, and this here would be B. Output equations could have a similar form shown here. We can basically relate these to a matrix equation as shown here on the right. Here's the matrix involving the state variables, and here's the matrix involving the input variables. And of course, these four elements constitute the matrix C, and these four elements here constitute the matrix D. All right, what about a nonlinear equation? So for example, if we look at these set of state space equations, you immediately realize that this involves the square of a state variable, which means this is a nonlinear equation. When we're dealing with nonlinear equations, we basically cannot work with matrix equations. It has no meaning because matrices are applied to linear systems. In this case, the second one is a linear equation. What about the output equations? Well, the first output equation is linear in x1, x2, u1, ut. Unfortunately, it's nonlinear in the second equation, y2, because of u2. It's u2 to the power of the fourth. So again, we cannot write this in the form of a matrix equation because we are dealing with a nonlinearity here. All right, so now let's look at the evolution in terms of how do we go about creating a small signal model for these set of system equations. So first thing we want to do is to perturb the input signals, which means u1 of t becomes u of 1, which is whatever the static value is. And this is the perturbation of that signal. U of 2 will have its static value, and of course you will perturb it as well. Now these are what we call input operating points. U12 and U2t are small input signal perturbations as a function of time about the input operating points U1, 2, and U2 respectively. All right, so that deals with the inputs. We also have to perturb the state variables and the output variables. So that means x1t becomes x1 uppercase plus small signal variation of x1, similarly for x2, similarly for y1, and similarly for y2. So these x1 and x2 are referred to as the state variable operating points, and y1 and y2 are referred to as the output variable operating points. So we essentially have outputs, variations, we have state variable variations, and input variations. So that's the starting point. All right, so the next step basically is to substitute the perturbed signal expressions into the original differential equations and output equations. All right, so what we've done is replaced x1 by x1 plus x1 hat. But if you take the derivative of this, x1 being a constant, you're just left with the derivative of the small signal with respect to t. And on the right-hand side, essentially all we've done is replaced x1, x2, u1, u2 by the steady state or equilibrium value and a perturbation, and that's the case for each one of these four. You do the same thing for the second state space equation. The x2 being a constant means that you only end up with the derivative of the small signal perturbation, that is x subscript 2. For the output equation, we do similarly the same thing. We have y1 plus y12, y2 plus y2 hat t, and then the x1, x2, u1, and u2 get replaced by the expressions that you see here. So what we're going to do now is we're going to approximate the functions on the right, that is for the differential equations and its output equations. We're going to basically approximate them by a Taylor series to first order, which means we keep basically the first order term, which will be a constant term, and the second next term would be basically involving first order derivatives. And if the signals u1, u2, x1, x2 are small enough with respect to the operating points, then we can essentially say that the Taylor series expanded to first order is sufficiently accurate, and we don't basically have to worry about second and higher order terms. All right, so here basically we're just showing the first order expansion, and so there's the first order term, and then of course we have x1, x2, u1, and u2, and so you can see perturbations with respect to input variables and perturbations with respect to the state variables, both for x1 and x2. And so this represents the operating point. This is changes in u and changes in x. And you'll notice that once you take a partial derivative, you hold everything constant except the variable that's being you're taking the derivative with respect to. But once you've taken the derivative, then u2 is replaced by its steady state value or equilibrium value, which is u of 2. And this is done essentially for all of the partial derivatives that have to be computed here. All right, what about the output equations? Well, very similar. Essentially, what we're going to do is expand this function to first order. And so there's an operating point. There's y1 plus y hat. This is the operating point, changes of x, and these are the changes with respect to u. Now, of course, we could graph various things. You look, for instance, does the output change for y1 or y2 with respect to changes in u1 and u2 or x1 and x2. And so this is just showing, say, for one combination with everything else being held constant, and you would have a graph similar to what we had discussed in a previous lecture. And so what you're doing is you're just making a small signal perturbation in the input. That input could have been a u, it could have been an x, and you're looking at the corresponding change in the output, which could have been a y1 or a y2. So same idea as before. And again, we're approximating basic things by a straight line. All right, so effectively this is like recycling the material from the previous lecture, but there are more combinations to consider. All right, so next step is basically the Taylor expansion to first order, but we're going to put it into matrix form. And why is that? Is because the derivative terms involve linear perturbations. So u1 is linear, u2 is linear, x1 and x2 are all both linear. So all of this can be represented in matrix form, as I've shown here. So a 2 by 2 matrix associated with changes in the input signal, and a 2 by 2 matrix associated with changes in the state variable. And so this matrix I'm going to call B of f, B subscript f, and this matrix I'm going to call J subscript f. So it's just another way of writing it. It's just in a more compact form, but can be done. All right, output equation, same idea. You can basically group things, and because it's linear and u1, u2, x1, x2 hat, we can basically write this out in matrix form, and so these are two different matrices, J sub G and B sub G. Right? All right, so now the procedure for developing small signal model using a 2-input, 2-state variable, 2-output variable example. So first step is to convert state variable equations into a state space form and identify the input variables, state variables, and output variables in the output equations. So one case considers a set of differential equations, output equations, which are given to you. The other possibility is a circuit diagram with input variables and output variables given, and what you need to do is, using the circuit diagram, determine the differential equations, the output equations. So this is an extra step that needs to be taken. This was an example that we had just discussed earlier in terms of first of all setting up the output equation and the state equation, but we did it for a single variable case. All right, having done that, the next step is to determine the equilibrium state variable operating points x1 and x2. It's the first step. We know what u1 and u2 are, which are the steady state values for the input variables, but we need to determine x1 and x2, because without x1, x2, we cannot determine the steady state or equilibrium points for y1 and y2. So this comes first, and then having computed x1 and x2 and knowing u1, u2, we can compute y1 and y2. Having done that, we can compute the Jacobian matrices, the 4 of them. Why? Because we have all the steady state points, and don't forget the Jacobian matrices involve partial derivatives, which are evaluated at the equilibrium points. And then 4 is to write out the small signal state space equations, which have this form, and the small signal output equations, which have this form. And then we can basically look at the original equations, which involve the steady state values with the perturbations. This would be the total. And on the output side would be the original values plus the perturbations in the output variables, which is the total. All right, so here basically we now show the small signal model for the status equations. And again, we have this plus this term, and then basically the small signal AC input, which is this one here. Now this term is going to be 0. All right, we just show. So effectively this will be, I could have written this as just this is equal to this and just say it's 0, but I left it here basically because it's an extension of what was done on a previous page. So because this is 0, steady state equilibrium is when there's no changes here, no inputs, and by definition then this becomes 0, and so this term basically makes no contribution at all. And so we're left with a small signal model which has this form here, and the matrices are the ones that you see here. So the whole problem of small signal modeling will be a two-step problem. One is to solve for x1 and x2, And the second step would be to compute these Jacobian matrices, given that you've computed the equilibrium points for x1, x2, and u1 and u2 would have been given. All right, then the output equation. So same idea. We have this. All right, but we know that the output variable equilibrium points, y1, y2, is in fact equivalent to this. So these two basically represent this combination, which means y1 hat, y2 hat is everything you'd see on the far right. So the small signal output equations will take on this form. And again, you can compute what these Jacobian matrices are. Once you've established what the equilibrium values for x1, x2 are, u1 and u2 will have been given. So that more or less basically takes you through the whole process. All right, so now let's consider, for instance, why is small signal modeling employed? There are a number of scenarios in which it can be used, but we'll be using an example here, which is more or less consistent with what you'll be discussing in ECE 231 this term. And so what we'd like to do is to understand the small signal behavior of a system at a given operating point Q. And we're using a transistor here as a case study. And we want to model the transistor behavior when used as an amplifier. Other options are, for instance, to model electrical cells at a particular operating current. So we'll just stick to this particular example. The notes have more examples involving applications in which small signal modeling is employed. All right, so here on the right is the circuit. And what we have here is some form of DC source. And we have a variable resistor. And we're basically varying this resistance to basically alter the amount of current that's flowing into the base of this particular transistor. This IB corresponds to these blue lines that you see. So by adjusting this value of RB, given the voltage is kept fixed, means that we're moving to different of these blue lines. All right, so for this particular blue line, basically now we would do is to essentially look at what is the relationship between the voltage between the collector and emitter, which is the voltage that's seen along the x-axis, and the collector current, which is the one that you're seeing through here. That's basically flowing into the node at C. And so if you adjust the voltage, right, then basically you'll see a change in the current. And so these are basically showing for a given driving current along here. If the collector emitter voltage goes up, let's say it goes to 32, then this would correspond to a current on the order of about 15 milliamps. Let's say we chosen 60. Well, let's take 60. And let's say we go to 12. Collector emitter voltage 12, that's the voltage across here. And that would basically be corresponding to approximately a collector current of 5 milliamps flowing into the collector node here for a base current of 60 microamps. All right, so these blue lines basically indicate making changes to the resistor and then seeing what those characteristic curves look like. The other thing we're looking at is basically what are the characteristics of the actual device itself. And so in effect what we've got is Kirchhoff's voltage law around this loop here. At this voltage minus IC times RC minus VC equals 0. All right, so if we're to look at that alone, this basically just becomes the equation of a straight line. If this is an open circuit, then the voltage that appears across these terminals would be the same as the terminal voltage, which is 24 volts, which is basically here. On the other hand, if this becomes a short circuit, then the current that flows through here is just 24 divided by 2400. That corresponds to 10 milliamps. And if you draw if you basically draw this curve, it's just a straight line that has this form, and this is the basically mathematical form of this equation. Now you might say, well, what is the operating point? Well, the operating point is basically the intersection between this red line and the blue line. All right, so in this particular case, you can see that this would be an operating point at this location here. This is one we've chosen. But there could also be an operating point here. So for instance, if the base current was 100 microamps, then this would be the operating point you'd be seeing, right, at this intersection between the blue and red line. In our example, though, it's here, at this point here. Okay? And so what we're going to be looking at is small signal modeling. And so that's equivalent to saying we're going to make small adjustments in this R base resistance, just as an example. So this would be called operating when we just keep its standard value, and then we perturb it up and down by a small amount, and this is this value RB that you see here. So the combination of the operating resistance, and the perturbed value of resistance is the actual value of resistance that you'll be seeing as a function of time. So this is more or less the type of problem we're looking at. We're wanting to see if we make a small change of resistance here, that amounts to a small change in current, how does that impact the amount of current flowing into the collector of this transistor? More or less what we're looking at is the amplification factor. All right, so finally what we'd like to do then with all this is to investigate the stability of a physical model about an operating point, and then design a controller that delivers robust regulation, which means fast response with any oscillations, and good tracking performance. That is, error between the requested value and the measured value is near zero. So these are things that are important when you're basically dealing, for instance, in the control of a system. We typically use small signal modeling to basically provide us with that necessary information. And again, as a reminder that small signal modeling is an important topic in EC231, which you'll be exposed to this term.